Martinez and I am with Group 1. This video will be talking about lab number 4. In this experiment, we'll be exploring how changing mass affects the acceleration in a system governed by Newton's second law. In this experiment, we will be exploring how changing mass affects the acceleration in a system governed by Newton's second law of motion. In our previous lab, we measured acceleration using a fixed set of masses. This time, we're intentionally increasing or decreasing the mass to see how the theoretical acceleration should change and how closely our real measurements match our theoretical predictions. Essentially, we're testing the relationship expressed in the equation acceleration equals force net over mass, which tells us that acceleration depends directly on the net force and inversely on the total mass of the system. In our physics lecture, this relationship is constantly supported. Newton's second law is one of the most experimentally verified principles in classical mechanics. Studies of motion show that when mass increases while the force stays constant, the acceleration decreases in a predictable way. This is why controlled mass and force systems, such as the air track that we will be using in this lab, provides a clean way to observe how theoretical models compare to real-world data. Understanding this relationship isn't just important to the classroom. It's the same principle used in real-life applications, where engineers must calculate how added weight affects the acceleration of a vehicle. This also applies to sports science, where athletes may use resistance training to increase either power or speed. Even roller coaster designers rely on these ideas to ensure that a change in mass, such as a full or empty train, still can produce a safe and reliable acceleration. In this lab, we're applying these well-established physics concepts to our own experimental setup. In this lab, we're applying these well-established physics concepts to our own experimental setup, testing how accurately our system follows the theoretical model and which factors cause deviations. Now I'll be handing it over to Daniela, where she will explain all the materials that we use in this lab and how we use those materials to conduct our own calculations.
Hi, my name is Daniela, and now I will explain the materials we use for the lab number 4. For this experiment, we used several materials to modify the acceleration of the system and analyze percent error and percent difference between our old and new results. First, we used an air track and a glider. The air track was connected to an air pump, which reduces friction by creating a thin layer of air under the glider. This allowed the glider to move smoothly and help us obtain more accurate acceleration measurements. We also used a pulley system attached to the end of the track along with a hanging mass. The hanging mass provided the net force that caused the glider to accelerate. In this experiment, we changed only one of the masses in the system in order to increase or decrease the theoretical acceleration, following the lab restrictions. Additionally, we used small metal masses to adjust either the hanging mass or increase the mass of the glider. All masses were measured using a triple beam balance to ensure theoretical calculations were as accurate as possible. To collect our data, we used a motion sensor connected to the Capstone software. The sensor allowed us to record position over time and calculate acceleration from the graph. Finally, we used a computer to run the Capstone program and analyze the data obtained during the experiment. All of these materials were essential for modifying the system mass, measuring acceleration, and comparing our theoretical and experimental results. Now, I will pass it to my teammate to explain the procedure.
Good evening. My name is David Maldonado. I am going to be discussing the procedure for lab activity for number 4. I want to give an apologies now. Unfortunately, I'm dealing with the throat infection, which is going to mess up my voice a little bit. So if my voice breaks or there's any errors with it, I want to apologize now. Our objective for this goal was to master percent error and percent difference. We're using the concept of acceleration to meet this goal. Our task is to change the acceleration from your previous experiment, and we will either be increasing or decreasing your theoretical acceleration using change in the masses. For our equipment setup, we have a couple restrictions. We can only change one of the masses, being either the hanging mass or the glide's mass. The mass of the glide can only be increased. The values you can add or subtract from the masses are discrete. You must adjust to the nearest value and recalculate your theoretical new values. Here we set up the table 1, which is the old values for acceleration, hanging mass, and glide mass from the previous experiment, and our new values. Our equations are hanging mass equals glide mass times acceleration new acceleration over gravity minus acceleration new. Glide mass will be equal to hanging mass times gravity minus acceleration u over acceleration u. We will be adjusting our masses if need be. We'll be calculating our new theoretical acceleration and the percent difference between our old and new theoretical accelerations. Now, for that equation, we'll use acceleration theoretical equals hanging mass times gravity over hanging mass plus glide mass. Our percent difference will equals reference value minus tested value over reference value. We'll be using table 2, which would be our old theoretical acceleration, our new theoretical acceleration, and our percent difference between the two. After processing our step 1, we'll be running our experiment enough times to get our smoothest position for the time graph that we can achieve. We'll change the measurements in our graph to the one we need to calculate acceleration. For step 2, we'll be calculating the percent errors for today's experiment. We'll be asking our questions: should your old and new percent errors be similar? Why or why not? Compare your percent errors. Are they similar? Does your percent error must be small or big, or does it not matter? Does it agree with your ideas in your previous experiment? Why? Do you need to rerun both experiments? Was either one of these experiments conducted with higher accuracy? What can be affecting your accuracy in any of these experiments? For step 3, we'll be calculating the percent difference between your experiment's old and new accelerations. Compare this value with the percent difference you calculate in the setup. We'll be once again using table 2 for old experimental acceleration, new experimental acceleration, and percent difference. Finally, we'll be reflecting on your following questions. Should these percent difference be similar? Why or why not? Compare your percent differences. Does it agree with your ideas in the previous questions? What can you include from these values, and why you use percent differences and not numerical differences to compare your values? I'll be passing it on to my next group member to discuss the portion of the experiment.
This is Alejandro for data and data analysis on lab 4. We're tasked to find the last lab's hanging mass, glide mass, and experimental acceleration. In this new lab, we either changed the hanging mass or glide mass and got a new acceleration. For us, we decided to change the hanging mass, which went from 0.015 kilograms to 0.010 kilograms. Our glide mass stayed the same at 0.1966 kilograms. Our experimental acceleration from last lab came out to negative 0.67, and our new one, we decided to set it at negative 0.38. With our new hanging mass in place, we're able to run a new trial to get different graphs on Capstone to get our new acceleration. For the new acceleration, we plugged in 2 points in the graphs and got negative 0.25 minus negative 0.06 divided by 5.15 minus 4.65, which gave us a total of negative 0.38, which is our new acceleration. Plugging that new acceleration into our percent difference, we get absolute of negative 0.67 minus negative 0.38 divided by negative 0.38 times 100, which gives us a percent difference of 76, which is over our hope of 30%. For our hanging mass, we calculated 0.1966 times negative 0.38 divided by negative 9.81 minus negative 0.38, which gives us a total hanging mass of 0.0079228. Using that value, we can plug it into our theoretical acceleration formula for step 2. We are tasked to find the percent error using the theoretical acceleration and the experimental acceleration. We plug in the absolute value of negative 0.4905, which would be our theoretical acceleration, minus negative 0.38, which would be our experimental acceleration, divided by negative 0.4905 times 100, which gives us a percent error of 22.528%. Step 2 also has a couple of questions. For the first one, should your old and new percent error be similar? Not necessarily. Since we have different hanging masses, our values are going to vary a lot and going to give us completely different total percent errors. Comparing our percent errors, they're not necessarily similar. For our first lab, we had a 0.3% error, a 3% error, and a 40% error. And for this lab, we had a 22.528%. So none of them are really too similar. For our percent error, it should be smaller, around 5% was our goal, which we had a little bit higher at 22, which wasn't too ideal. Rerunning both experiments would help us find better values, more accuracy, and maybe negate some of the interference picked up from the reader. We saw a lot higher accuracy in the first lab, having a lower 0.3% and a 3% error compared to our 22 from this lab. Some things that could have affected our accuracy could have been some interference with the reader. For step 3 of the lab, we were asked to get 2 different percent difference totals. For the first one, we were tasked to use the old theoretical acceleration and the new theoretical acceleration. And then for the second one, we were asked to use the old experimental acceleration and the new experimental acceleration. For the first one, we plugged in the absolute value, which gave us a percent difference of 41.632%. For the second percent difference, which gave us a total of 29.079% difference.
After multiple attempts, trials, and calculations, we ended up deciding to use the glide mass equation instead of the hang mass equation to help us calculate the theoretical acceleration, which helped us further calculate the error percentage of our lab and compare that result with the previous lab.